So now it is the next session time. Until now, we have been fascinated by the power and capability of small-scale optical sciences. Let me call it in that way. So we heard about the nanofabrication technology and fundamental quantum optics. Monica just gave us an insightful talk about quantum optics and quantum physics. So indeed, light is so fast, so precise. Nanometer is a very common unit in optical sciences. However, that is not all. Let me tell you. So now it is time to look at the large scale aspect of the optics, which is astronomical optics. So Large Binocular Telescope, LBT, is the largest single mounted telescope on Earth today. There is nothing bigger than that. And today we are so fortunate to have Dr. Barry Rothberg and Dr. John Hill, who are the astronomer and a technical director at LBT. So they will let us learn the power of large optics for astronomical science applications today. So with that, John and Barry, please let us see the capability of LBT. Thank you.
Okay, I'm going to start with a brief PowerPoint presentation about history. And then we're going to show a video, and then Barry is going to give a presentation.
We see it very well, John.
Oh, all right. So fasten your seatbelts because we're going to do history at a rate of 30 seconds per year.
We are ready. Thank you, John.
So LBT is two 8.4 meter telescope apertures on a common mount. That's equivalent to a circular aperture of 11.8 meters. Or if you phase across the long baseline, 22.65 meters. That means at 2 microns, you can make a resolution of 20 milliarc seconds with suitable phasing and adaptive optics. LBT is optimized for near UV through mid-infrared wavelengths. Mid-infrared to astronomers means 10 to 20 microns. And we have integrated adaptive optics, and we have both Gregorian F15 and prime focal stations. So this is the work turning the ground into a telescope pier in April of 1997 on Mount Graham. 3 years later, the telescope is starting to take place in Milan, Italy, where the steel structure was fabricated. This shows the azimuth frame of the telescope, what you might call a fork of a regular telescope mounted on the azimuth ring, showing the hydrostatic bearing. So the whole telescope floats on a thin layer of oil about 50 microns thick. Meanwhile, back at the Mir lab at the same time, we are just finishing the casting of borosilicate honeycomb mirror number 2 for LBT. And the polishing is underway for borosilicate honeycomb primary mirror number 1. At the Mir lab, the mirrors get polished with this stressed lap. There's interesting things is I don't have many pictures older than 2000 because that's when we got digital cameras. So it's much easier to store the pictures on my computer. Once the telescope parts were finished, they got put in very big boxes and sailed down the Po River to the ocean. And then about a month later, they arrive at the telescope base camp in Safford. Note that when we unpack all these huge number of telescope parts, more or less every dog in Safford got a new doghouse from all the leftover plywood. Then we go up to the mountain where that pier has turned into a whole enclosure in the intervening 4 years. And we start installing the telescope parts. This is the sections of the azimuth ring. Note that this ring was machined, assembled, and then the joints are pinned so that when it gets reassembled and you reinsert the pins, the steps between the segments are only a couple of microns. And we get rid of the last couple of microns by taking a stone and rubbing over it to smooth out the little edge between the segments. A thing that you never see if you go on the telescope tour today is inside the azimuth ring, there's a cable chain that brings up cooled water and power and data fibers from the fixed building onto the rotating telescope. That's the whole azimuth ring and cable chain together. Then we start bringing up the segments of the azimuth frame, the next piece up. Then the C-rings that make up the elevation axis. So the azimuth ring makes the azimuth axis, and the two C-rings make an elevation axis. This was the heaviest thing to come up the road, but not the widest. So it could still go horizontal. And we bring the pieces up through the hatch. So there was an external crane to assemble the building, but after the building was assembled, it's an internal crane that lifts all the parts of the telescope up from the ground floor and installs them on the telescope. There's the three sections of the azimuth frame together. Now you see us putting on the second of two C-rings for the elevation axis. The partners in LBT are 3 universities in Arizona for a 25% share, 25% to a group of organizations in Germany, 25% to Italy as a national project, and then the last 25% to a group of other US universities organized by the Research Corporation here in Tucson. Back at the mirror lab, we're installing mirror support actuators in the telescope cell. These honeycomb mirrors are stiff, but they're not infinitely stiff. So you have to support them in 160 places from the back of the mirror to hold the surface shape within sort of 30 nanometers as you move around the sky under different gravity and wind loads. So these pneumatic actuators are what do that. And the last thing before the mirror leaves the mirror lab is it gets put in its real telescope cell. We test that the actuators and their software work, and we measure the shape very carefully under the test optics and null lenses at the mirror lab to tune the final shape and adjust the actuator forces. Then that cell and the mirror in a separate truck, not in the cell, have to go to the mountain. This is the box with the mirror in it. This is now the widest thing that goes up the mountain as a 9-meter square, but the mountain road isn't 9 meters wide everywhere. So it has to tilt up on edge. And it takes 3 days to cover the 48 kilometers on the winding mountain road. Note that there's a trailer with 6 rows of axles with 8 wheels each. And each of those are hydraulically steerable and tiltable. So there's a truck driver, and then there's a guy riding on the trailer, running the trailer hydraulics. And then there's a guy pushing with a front loader in the back, plus a supervising engineer riding in the bucket of the front loader. So it's a big activity. Once we're on the mountain and we take the lid off the box, then we use suction cups to pick up the mirror glass and put it into the telescope cell again. This is where you test your faith in physics, because only the air pressure or the vacuum is holding the mirror up. And on the mountain, that's 2/3 less or 1/3 less than it was in Tucson. So you have to make sure you don't have any leaks and keep your fingers crossed as well. So we installed 1 prime focus camera in front of the primary mirror and 1 primary mirror in June of 2004. There's the primary prime focus corrector. It's a six element corrector that corrects a ½ field of view. Here's the first engineering star. This is Polaris imaged with no coating on the primary mirror. Polaris is bright, so there are plenty of photons. And then this is after we coated the primary mirror in October 2005, the first pretty image of a galaxy. So here's coating the primary mirror. This is a couple of years later when I had more time to take pictures. So we clean the glass surface, and then we mount a vacuum bell jar on the telescope, pump out the air, and then we evaporate aluminum onto the glass surface. There's no need to take the mirror out of the telescope. It's much safer and easier to move the bell jar to the telescope than to take the 8.4 meter mirror down. You'll see more of bell jar things in the video. There's an adaptive secondary. Here's a close-up view. It has 672 voice coil actuators. It makes a spectacular PSF with a very nice looking airy pattern. This is what the optical path looks like when we combine the beams from the two sides of the telescope. So parabolic primary mirror, Gregorian secondary mirror, flat tertiary mirrors, and then a sequence of beam combiners in either the LBT instrument or the Link Nirvana instrument that are both interferometers. There's LBT showing that beam combining in live life. And there's an image of first fringes where we get the diffraction pattern of the full telescope. And with that, I will stop, and I think Barry is going to show the video. Is that right, Barry, or am I going to do it?
Barry, you are muted. Would you unmute, please?
Yes, sorry. Yes, I will show the video, and I just wanted to say hi with my assistant astronomer, Rigel, who provides support to a lot of our observers during nighttime operations. So I will use the advanced feature on Zoom, which I just discovered today, to upload a video. This was put together by students in the astronomy department under Chris Impey. This was filmed on location. Myself and Mike Wagner, who's one of the mountain managers up there, provided a tour for the students. And we drove up and spent the day through sunset at night and gave the students a chance to see how operations proceeded. So with further ado, I will begin.
This is 78 Delta. Is there any downhill traffic on the access road? Over. Negative contact, one vehicle proceeding up the access road. Occasionally someone will respond or make a call while I'm on here, and then you get on there and say, you know, negative, there's one vehicle proceeding up or down, please be advised. So we're currently located in the high bay, which is a storage area, as well as a means by which we can transport instruments up to the telescope. Above us in the high bay are these giant doors, and we can transport instruments and material through those doors to the telescope. Behind me is one of our two mods, which is a multi-object double spectrograph. These are imagers and spectrographs that can take data at wavelengths that are visible, that our eyes can see. Currently they're off the telescope for refurbishment, and they'll be reinstalled on the telescope in early October. The large red object is the bell jar. This object is used to help recoat and make the mirror nice and shiny and reflective. So essentially the bell jar is moved up through the high bay doors. It's put on one of the two mirrors. A seal is created, and then what happens is pressure is applied, it's evacuated, and we actually are able to recoat the mirror to make it nice and shiny and clean and able to collect lots of photons. A lot of containers in the high bay here are the remnants of Link Nirvana, which is our newest instrument. This was built in Heidelberg, Germany, and shipped all the way from Germany to Mount Graham. Link Nirvana is an infrared imager that uses multi-conjugate adaptive optics to help clear the sky up, basically make the sky less turbulent. So very simply, it works by lots of little detectors, look at little stars, they measure how the stars are moving around, and they make a lot of mirrors compensate for that, so you get a nice super sharp object and super sharp resolution, even better than you get from the Hubble Space Telescope.
Okay, we call this the bogey level. This is the level where the wheels that support the rotating structure resides. They sit on this track. There's 4 stations, 2 6-wheel, this is a 6-wheel station, and 2 4-wheel stations. And these 4 stations support roughly 2,000 tons of the building, the weight of the building. The building rotates on this outer pier, the telescope rotates on this inner pier.
So we are on the floor of the Large Binocular Telescope, the world's largest optical and near-infrared telescope. The telescope is configured almost the same on both sides. We have the primary mirrors, we have the large binocular cameras, which are, we call it prime focus. So the photons from the sky hit the primary and they bounce up and they go directly into the large binocular cameras. So for instance, if we were to start tonight's observing with the LBCs, then the secondary arm you see, which is what we call in the beam, would be moved out of the way, and we move the large binocular camera into the beam. When we use LUCI or MODS, which are optical and imager spectrographs, one is optical, which is MODS, and one is in the near infrared, which is LUCI. Then we move the large binocular cameras out of the way, and we move the swing arms for the secondaries into position. There's also a tertiary mirror. And if we use LUCI, which sits in a position between the 2 primary mirrors, the tertiary mirror will swing into position so the photons can be directed into LUCI. The 2 secondary mirrors which are being used currently are what we call adaptive optics secondaries. They have 1 meter or so in diameter, and they have controls in them which actually very rapidly change their configuration. So when we're in adaptive optics mode, and we use this with Lucifer, this very quick motion of the mirrors is used to compensate for the turbulence in the atmosphere. So if you ever looked out on a night, you can see lots of stars, and you see the stars dancing, this is the atmospheric turbulence. And so the less the stars dance around, the much better it is for astronomical observations. And the only way to really beat atmospheric turbulence is to compensate for it or to go into deep space. One thing we need to do on a daily basis is to refill the dewars to keep the instruments cold. So the large binocular cameras, for instance, need to be filled daily, as do the MODS imager and spectrographs. Before we start science observations, we tilt the telescope to horizon so it's easier to reach the LBCs. The little cart has a scissor lift. We go up, refill the dewar, and then bring it back down. To refill MODS, we keep the telescope at zenith so that the MODS which hang off the back end of the primary mirrors can be filled directly. Also attached on the telescope are several different items to help observing. One of which is the DIM monitor, which is basically a differential image motion monitor. It's essentially, you think of it as a small telescope with 2 apertures, and what it does is it measures, it fixes on a star and compares the motion of the star in the two apertures. And from that, we're able to tell just how steady the atmosphere is, just how much turbulence there is. And depending on how steady it is, we use that as a guidepost to determine what kind of programs one should be observing for the night, and if perhaps adaptive optics would be useful for observing for that night. We also have a laser guide star system, which we call Argos. This is what we call a ground laser adaptive optics system. It's 6 lasers, green lasers, which create artificial stars in the sky. And those lasers are actually attached to the upper structure of the telescope. And so in situations where we want to use adaptive optics and the lasers, we actually would fire those lasers into the sky and then be able to track the motions of these fake or artificial stars. So one of the other things that we have to keep in mind as things come on and off the telescope, as we get new instrumentation, is that we have to keep the telescope balanced. That is, the weight has to be distributed properly, otherwise the telescope won't be able to track or move smoothly. So what we have is a dynamic balance system. Essentially, we have several large glycol tanks situated throughout the telescope, and then we can redistribute weight in those tanks depending upon what instruments are on or off the telescope. And this can be done fairly quickly, and it's usually done if any major changes are done. For instance, if we have to service an instrument or if we're installing an instrument. We use glycol because if we use something like water at cold temperatures, it would freeze. Glycol remains fluid at very cold temperatures.
So one of our biggest advantages is we can reconfigure the telescope within 20 minutes or less, depending on what configuration, simply by going to a GUI and clicking a few buttons. It really gives us an advantage in the astronomy world over other telescopes, where it may take an hour, a day, or the same amount of time, but much more manpower.
Well, we are in the LBT control room, so this is sort of the heart of the operation during the night. So behind me we have David Gonzalez Huerta, who is our telescope operator for tonight. So he's in charge of making sure all the complicated systems work correctly, the telescope can move. Along the row of computers here are what are called our OB stations. Normally when we have visiting astronomers observe at the LBT in person, they'll be using these workstations to run the instruments. So these will be the ones that will control the data and where we're pointing and take the information from either the LBCs, mods, or LUCIs. Tonight we have our service observers down in Tucson observing from our remote observing room on the 5th floor of Stewart Observatory. So if you look at the screen behind me, you can see several of our service observers there. Over here is we have the big board, which gives all the information as to what instrument is authorized, and by that I mean which instrument is basically running the telescope and captures all the photons. So that's in the optical path, where we're pointed, scene conditions, weather, etc. So this is where you would spend pretty much all of your night on a good night of observing.
All right, so I don't know if anyone had any questions before the video, after the video, but I do also have a presentation which I'll discuss some of the instrumentation, adaptive optics, and then give a little review of some highlights of science that we've done at LBT recently. If not, then I will share the screen. I'm assuming everyone can see the screen all right without any issue?
Very good, very.
What?
Very good.
Okay,
We
great.
see it very well.
So as we've seen here and in the videos and John's discussion, this is the LBT. This is a schematic diagram, one that was actually published in Popular Mechanics and another provided to us by one of our partners. And you can see the distribution of the instruments and of the telescope with a comparison with a person on it for scale and for size. So all of our instruments are mounted all the time, and we have the ability to switch between the instruments during the night. So we're not locked into using one instrument for the entire night. And often for observing, we will switch a couple times, 1 or 2 times, even 3 times during the night, as required by science. So as you can see here, one of the differences from other telescopes in the world is that we have 2 primary mirrors. the SX, which is on the left side, and the DX, which is on the right side. One of the questions I saw in the chat was, whether we can use them as independent telescopes. So we sort of diagram this out down here. In many cases, what our observers will do is they will configure the same configuration with the same instrument on each side. So, our facility instruments are twinned, so to speak. So there's 2 Lucys, 2 mods, 2 LBCs. So we could, for instance, configure the Lucys, which are the near-infrared optical imager, near-infrared imager and spectrograph, to the same configuration. And so we would point at the same place on the sky. However, we do have the ability to move each of the mirrors independently to within what we call this co-pointing limit. In angular description of it is about 40 arc seconds difference between how we can move the 2 mirrors. So for instance, what we could do is we could do imaging on one side, spectroscopy on the other, and one of the mirrors could move a little bit for dithering purposes while the other remains fixed in place. This gives us a lot of flexibility so that we can just, depending on what the science calls for, we can try different things and cover as much science and breadth as we can during the night. A lot of this is quite complicated, and we have something called the pointing control system, which determines how to process the request. So for instance, we have a science target, we decide to move to the target. The PCS determines how the telescope, the mount itself, and how the mirror should be positioned depending on what it is we're configured to do and what we'd like each side of the telescope to do. So for instance, with the optical spectrograph mods, we send what we call a preset, which is the coordinates to the target. The telescope moves to the target. And if, for instance, something happens on one side of the telescope, for instance, the guide star, which is used to maintain a fixed position in the sky, doesn't appear, or there's a problem, one side of the telescope could actually continue and proceed with the science while we get things going on the other side of the telescope. And this allows us the capability so that we don't have as much significant downtime, right? One side doesn't work, we don't lose or have the ability to lose time because of that one side of the telescope. So I want to go into a little bit of the facility instruments. We now have 4 facility instruments. We've added 1 recently, and that's fully transferred for what we call a PI instrument, which was a principal investigator instrument. That is, it was built by one of our partners, and basically you had to go through that, permission with the people who built the instrument to use the instrument. That is now changed to what we call a facility instrument, which is something that's available to all the partners all the time. So first of them is the large binocular cameras. These are the ones that are mounted at the prime focus, and the field of view for these are about 1/2 degree, or about roughly just a shade under the size of the full moon on the sky. So here, this is the set of 4 CCD chips, which make up each of the LBCs. So it's the same configuration on each side. And this is sort of a distortion map of the LBCs with the optics and the CCDs. So you can see how much distortion there is as a function of radius from the pointing center. As an example, this is a galaxy IC342, which is a spiral galaxy somewhat in the plane of the Milky Way. And you can see how the size of the galaxy fills out the field of view for the LBCs. The 2 of them are optimized for different parts of the wavelength. So the left, or the SX, is optimized more for blue wavelengths, near UV up to about 5,000 angstroms, which is about what you see with your eye. On the red side, the right side is optimized more for red observations, taking us all the way out to about 1 micron in wavelength. The second instrument is the multi-object double spectrograph. This is what we call MODS. These are mounted at the direct Gregorian port. So this is actually, you can see the image here, behind the primary mirrors. There's basically a hole there, and the MODS go into that hole. So the tertiary moves out of the way, and basically the secondary mirrors point directly down the light beams into MODS. I put up a schematic diagram of how the light comes into MODS. There's a red and blue collimator which separates the beam. So each of the 2 MODS has a red channel and a blue channel. So in some respects, if you wanted to say do imaging with MODS, you could actually image 4 filters, 4 separate wavelengths at the same time using both mods on both sides of the telescope. Mods, though, is usually used for spectroscopy. We can get a resolution of about 2000, and there's also a prism mode for very low resolution, but to get a lot of objects in the field of view. In addition to just sort of a standard spectroscopy, so a lot of other telescopes, you have something called a long slit. So basically you put this single slit over your object. It blocks out all the other parts of the sky from the object of interest. The light goes through the slit. The grating disperses the light, and you can get spectroscopic measurements of all kinds of atoms and molecules. We also have the ability to create what we call a custom mask. That is, we can take a sheet of metal and cut into that metal different slits to match a configuration of whatever you're looking at the sky. For example, if you're looking at a cluster of galaxies and you wanted to get spectra of each galaxy in this cluster, you could design a mask with slits that correspond to each of those galaxies and put them in each mods. That way you can get 12, 25, whatever number of galaxies or stars spectra simultaneously from both sides of the telescope. So the next 2 facility instruments, third one is Lucy. The moniker for Lucy and what the acronym stands for has changed over time. Now it's the LBT utility camera in the infrared. At one point, it had been thought that it might include an integral field unit in it, but instead it has imaging capabilities and long slit and multi-object mask capabilities. So there's a CAD diagram. I think it may, I'm not sure of this program that was used. It gives you an idea of the 3-dimensional insides of the instrument. This is actually one of the Lucys. I believe this is Lucy 2, separated out in the lab, and you can see its constituent parts. And this, like mods, it has what we call a custom design multi-object spectroscopic mask capability. So you can put a set of masks in there, and there's this arm that will move into place in the focal plane. It will move in and out the facility long slit, so you can have a single long slit of different widths, and the resolution will scale with the width. Or like with mods, you could design masks that match, say, a cluster of galaxies, a cluster of stars, and then it will move it into place and then disperse the light from each of those slits in there. Lucy is cryogenically cooled. So this is a picture of the MOS unit warmed up, but all of these masks, all of the electronics, everything is cryogenically cooled when it's attached to the telescope. Lucy is used for the near infrared, which goes from about 0.9 microns to about 2.4 microns. And so you can get all kinds of interesting absorption and emission line features. A lot of people use the Lucys to look at higher redshift or more distant objects. So things like optical lines like H alpha or lines that we would see with our eyes would be redshifted at higher redshifts into the near infrared. And we have the ability to have about 23 of these custom masks in at any time. What we try and do is we will then have what we call a mask exchange. So throughout the semester, several times, we will remove the masks from each of the Lucys and put brand new masks in there that are designed by our users in the LBT community. The newest facility instrument is the Pepsi instrument. And no, there's no trademark infringement. It's the Pot-Saint-Michel polarimetric spectrometer instrument. This is a very high resolution Echelle spectrograph. These are mounted. So Pepsi has 2 capabilities. The first is this high resolution Echelle spectrograph. So it's the fiber unit, they're mounted on the edge of where the primary mirrors are. So I can go back to the schematic here. So the Pepsi, one of the PFUs are mounted here, and here are the primary mirrors. But Pepsi also has a polarimeter, which is attached in a separate place. So the PFUs give the capability from a resolution from 50 to 250,000. They're sensitive in optical wavelengths from about 0.3 to 0.9 microns. It's also an instrument that allows us to use, you can connect it up to the Vatican telescope, which is a smaller telescope down the road. And there's also a solar monitoring telescope, which is on the balcony of the LBT. So you can basically switch between each of the 3 telescopes. So for instance, if we're using LBT at night for say Mods or Lucy, they could use the VAT to take data at the same time. We've also taken data during solar eclipses to get high resolution shell spectroscopy of solar eclipses. The second capability is polarimetry. So in this case, what happens is the mods are actually removed from the telescope here, and instead the Pepsi polarimeters are installed at the direct Gregorian port. And this gives the ability to get high resolution spectroscopy for all 4 Stokes parameters. So currently, we're actually in the middle of a Pepsi polarimeter campaign. So the mods came off in late December, and until about mid-January, we're actually doing polarimetric observations every night at LBT. So things like magnetic fields of stars, you can even do that for, say, AGN, all kinds of amazing high-resolution stuff that really can't be done anywhere else with any other observatories. So one of the unique capabilities of LBT is our adaptive optics systems. So now a lot of telescopes have AO systems. This is not a new technology, but the difference between our AO system and other AO systems is that ours actually incorporates the secondary mirrors. A lot of other telescopes like Keck, for example, their AO system is actually a bench that you take the light off from the telescope and then it goes to this bench of optics, and that's your AO system. Here, we're actually moving the secondary mirrors in real time to compensate for atmospheric turbulence. So as John mentioned, there's some 670 actuators on the surface of this deformable mirror that will move it at high rates of speed in order to compensate for atmospheric turbulence. So we've put in here, this is our ray design for the light coming in from the hexapod. It goes to the tertiary mirror, and then it goes into either Lucy or LBTI. These are our 2 instruments that primarily use the adaptive optics system. So this is another picture of the adaptive secondary itself. And this is a thin shell down here. And you can see all the actuators here, as well as the complicated electronic system that controls everything. A second part of the system, in addition with the adaptive secondary mirror, or ASM, is the wavefront sensor system. So what happens is that the light from the secondary hits the tertiary, and then it goes into a dichroic, which basically splits off the light. So light wavelengths greater than, say, about 0.9 microns will go into Lucy, and wavelengths shorter than that will go into the wavefront sensor system. It'll get split up. One of them, we have an acquisition camera so that we actually can acquire the star. So when we move the telescope to your science target, let's say, for instance, it's a bright active galactic nucleus. You would center the active galactic nucleus in the acquisition camera. And then the light is also split off into the wavefront sensor camera itself, going through a pyramid wavefront sensor. And then you get a pupil image from that. And from that, you can then, the system, the software, the control system calculates what the corrections that are needed to compensate for atmospheric turbulence. This is sort of a cutaway of the complicated wavefront sensor system here. So here's the pyramid wavefront sensor. This is the wavefront sensor camera. And over here is the acquisition camera. So the light, similar to the schematic here, comes in, and then it's split up. And so, as I said, here's the acquisition camera, and then here's the wavefront sensor camera. And then here is Rigel at work at night, making sure our Lucy adaptive optics system is working correctly and getting ready for some interesting science. So both Lucy and LBTI use the AO system. LBTI has a much broader wavelength coverage. You can go out to about 13 microns. The main difference between Lucy and LBTI in a technical sense is that Lucy has a instrument rotator. So when you track an object on the sky and you decide you want a fixed position angle on the sky, Lucy will keep it fixed in place. LBTI does not have a derotator. So because we're using an alt-azimuth telescope, things will rotate on the sky. And so the images in LBTI will actually rotate over time. So I'm going to get to some of the more interesting science here. So I've sort of broken it up a little bit based on our facility instruments, and these are by no means a comprehensive overview of some of the science we do at LBT, but some of the things I thought were actually quite interesting. So the first is something that came out recently, you might have seen press releases on it, was the discovery and determination of the composition of a quasi-satellite of Earth. So this is an object captured by the gravitational potential of the Earth that's going to remain basically a moon of the Earth for a few hundred years. So this is a campaign that began with its detection in 2016 and several years of follow-up observations using both LUCI and MODS. So we took both images and spectroscopy with LUCI and MODS. So this movie right here is actually taken from a series of MODS images. And we were able to, you can see all this things moving here in the background. These are galaxies and stars. And so we basically set the telescope, what we call a non-sidereal setup, so that it keeps the object, which moves at a rate different than the rotation of the Earth, fixed in the focal plane. So this is actually this quasi-satellite itself. And here is a reflectance spectra of it. And essentially what this spectra shows is a comparison between the points, these points here, taken from LUCI and MODS, and the regolith from the lunar surface. And the end result is that what we think happened is that a piece of the moon broke off, was captured by the gravitational well of the Earth, and is actually now a quasi-satellite of the Earth. So it's actually pretty cool. Again, LUCI and MODS do a lot of work well together. This is the discovery of the first triple AGN. So this is three galaxies that are merging together. So each of the galaxies, there are 3 nuclei. And using both optical and near-infrared spectroscopy, we were able to determine that each of these 3 points contain a supermassive black hole that is accreting a lot of material and showing broad emission lines or high excitation lines that you can only produce from the accretion disk of a supermassive black hole. And it was the first confirmation of a galaxy in which there were 3 AGN present. So this was actually something that both of these are something that I was a part of, and just wonderful capabilities of LBT. So adaptive optics. These are some of our adaptive optics results. The top is a movie showing the Io being eclipsed by one of the other moons of Jupiter. During this time series eclipse, you can actually see these hotspots. These hotspots actually correlate to places with volcanic activity on the surface of Io. So the brightest of this is the Loki Patera. The interferometry, so this basically combined both of the mirrors together to give normally it would give us a resolution of about 60 to 70 kilometers, but using this capability by actually time sequencing of the passage, I believe it was Europa, in front of Io, you can actually increase your resolution because you can actually figure out the time it takes to occult different portions of the surface of Io, and then do calculations of things like the heat and actually map out the hotspots on the surface. So this is a reconstruction from the LBTI data compared to a geological map from one of the Voyager spacecrafts. And you can see the resolution from the ground is actually quite good compared to actually a satellite in orbit around Io. This is some results from our recent LUCI verification time with the adaptive optics. Here we have Uranus along with the rings. This is a false color image. So we combine 3 filters from the near infrared. This red part is about 2.2 microns. And this J and H are predominantly seen as 1.2 and 1.6 microns. And here are direct images of exoplanets around the star HR 8799. So this is an observation that had been done before, but it just demonstrates some of the capabilities of AO with LUCI that were actually direct imaging planets around another star. Some interesting observations and science results from Pepsi and from the LBCs. So here, what Pepsi has done is done something called Doppler imaging to actually reconstruct star spots on the surface of another star, 2 Pegasi. So here we actually have these star spots and a color table representing what these, the temperatures and the locations of the star spots. And these data are also taken with the polarimeter on. So we can actually measure the magnetic fields around these spots. So this is probably one of the most highest resolution and deepest kind of observations of a star outside of our sun, in which we can actually map out the presence of the sunspots as well as the magnetic fields of that star. And then some interesting results from LBC. So here we've actually been able to track objects with the LBT. The top is OSIRIS-REx. So you may remember this is the mission U of A was a large part of. It did a retrieval from an asteroid. But in order to get to that asteroid, it had to do a gravitational slingshot around the Earth a few years ago. And so, we knew it was coming. A lot of telescopes planned to sort of track it in the sky. We were actually able to get on it and detect it 2 weeks before any other telescope because we were able to, because of the capabilities of the LBT. So here we are 2 weeks before anyone else actually tracking OSIRIS-REx. And this down here was another fun object. This is another quasi-satellite, but as it turned out, this is not something blasted off from the surface of the moon, but was actually the spent stage of a Centaur rocket launched in the 1960s that we were able to track using the LBCs. The deep imaging capabilities of LBCs are also quite useful to some of our partners. This is an example of a dwarf galaxy. So here we have from the Sloan Digital Sky Survey, sort of deep images. You can see this fuzzy blob here. This is a dwarf galaxy, something that's about 3 orders of magnitude less massive than our own Milky Way. It was thought to exist in a void, that no other galaxies, nothing really was going on around it. But with deep imaging from the LBCs, we actually were able to determine that there's a tidal tail, meaning it had undergone some sort of interaction. And that closer up, you can see there's actually smaller little bits, smaller satellite galaxies. So with the LBCs, with a lot of deep imaging, we were able to determine not just that this isolated galaxy had, in what we thought was an empty region of space, had undergone interactions, but it actually had its own smaller satellite galaxies around it. So this is just a highlight of some of the interesting things that we can do at LBT. So I will stop sharing, and if there are any questions,